So we'll take a step back from networks and go back to just graph theory. There's a few different sort of types of graphs. I'll call these types. I don't want to use the term family yet. That means something else we'll talk about in the activity. So I mentioned this term, a simple graph. A simple graph is exactly as I've described it, as I defined a graph. It's just a set, and now we have to be really technical. It's a set of vertices, not a multi-set. So we don't have the same vertex appearing multiple times in the vertex set. Every vertex is distinct. And a set of edges. Again, not a multi-set. That means that an edge that there's never more than one edge between the same pair of vertices. So notice every edge connects two distinct vertices, and any pair of vertices has at most one edge between them. So that means there's no multi-edges. Those are edges that connect the same pair. And there's no self loops. An edge doesn't connect a vertex to itself. We'll see examples of that in a second. And also, there's no direction to the edges. Exactly as I described it before, I don't care if A connects to B or B connects to A. I just care that A and B are connected in a simple graph. Let's move. One other thing I want to look at here. We'll see an example in a second about one in which edges are directed, and we have different terminology and a different name we'll give to that type of graph. Okay, so these are simple graphs, are these guys. One other piece of terminology I'll throw at you here. Notice this is just one graph. Let's call this graph, I don't know, let's call this whole graph H. That's this entire thing. Notice that there are two vertices here that are connected to each other, but to no other vertices in the graph. That is, I can't find a sequence of vertices in which each subsequent such that the vertices are sequentially connected together. I can't get from, say, this vertex to this vertex via a path, via a sequence of edges. There's no way to do it. What we say is this is a disconnected graph. So I'll throw that term at you today. This is a disconnected graph, and it has two components to it. It has two connected components. We have this big component here that takes up the majority of the graph, and then we have this component here, which is just those two vertices by themselves. So this is, let's call this, I don't know, component 1 and component 2. And the reason why I want to introduce that early is because in network science, we just have a bunch of data and then we look at the network that comes from that. A big thing is going to be determining if that network is connected or disconnected and the size of the components. That'll be a real interesting part of this course. So we talk about this phenomenon called the giant component of a network. In graph theory, there's some discussion of components and disconnected graphs, but for a lot of the stuff I've worked on, we usually focus on connected graphs. It's a hypothesis in many theorems that the graph be connected. All right, again, don't want to get too deep in the weeds, but yep, okay. Components, and here's a graph. I don't need to have labels, as you can see. I don't really need to have labels on the vertices. I can just kind of draw the graph with vertices and edges. Yeah, that's my point. We don't need to actually have a set of labels for these. All right, well, let's talk about some variations on this. Again, this is a simple graph. And in this case, it's a disconnected simple graph. Multigraphs are graphs in which you're allowed to have multiple edges between the same pair of vertices. So if you take a look at, say, this vertex and this vertex, there are three edges that go between those. So let's say this is called vertex A and this is called vertex B. Then the edge set would include AB 3 times. And so that means that the edge set is actually an edge multi-set, to be technical about it. Multi-sets allow for repeated elements of the set, and those are listed out as many times as they're there. So that's a multigraph. These will show up and can be used to model certain situations. We might want to use a multigraph. Yeah, not all of the pairs have to have multiple edges between them for me to consider it a multigraph. I just need at least one pair has more than one edge between it, and then those are multi edges, and the graph is called a multigraph. Okay. And in that case, yeah, we have to be a little bit more particular about how we define the degree of a vertex. Before, I think I said it's the number of neighbors that a vertex has. Well, with multigraphs, we usually want to know the multiplicity of the edges. So not just the number of neighbors, but also, more accurately, how many edges are incident with a particular vertex. So here, A is incident with 1, 2, 3, 4, 5, 6 different edges. And so in many situations, we would say the degree of A is 6, counting all of those multi-edges. There may be situations where you do just want to count the number of neighbors in a multigraph. So we'll have to describe that. It won't be clear from context what we're talking about. Point is, when we go to these variations of graphs, things get a little bit more complicated, and we have to be clearer about what we're talking about. If I just say degree, I need to tell you what kind of degree I'm talking about. A pseudograph allows for self-loops. So that means, let's again take an example. Let's call this vertex A. That means AA would be an element of the edge set of this graph. Let's call this graph F. I'll name it F. It means AA, that edge, would appear in the edge set of this graph. So that means that edges do not have to connect distinct vertices. They can connect a vertex and itself. There are situations, I can think of some modeling situations where we would want to allow for this to happen, these self loops. So we call these pseudographs. This is a disconnected pseudograph because I have this component up here and another component down here that just consists of a single vertex connected to itself. So that's a pseudograph. The last sort of big type of graph is digraphs. So we call these directed graphs or digraphs. And in this situation, it means that the edges have a direction. So here we have a bunch of vertex names. So that means, say, my edge set here. What should I call this one? I don't know. How about G1? I'll call this graph G1. The edge set of G1. We have to be careful now, if we're working with a digraph, to make sure our edges are ordered as they should be. So, for example, this edge goes from 2 to 1. So that means oftentimes we would represent directed edges with parentheses to indicate that it's an ordered pair. So 2, 1 is a directed edge, sometimes called an arc, 2 to 1. There's also an arc from 1 to 2, so that's also in the edge set of G1. There's an arc or a directed edge from 2 to A, so 2 to A is an edge, so on and so forth. There's one from C to 2. There's one from 7 to 2, and there's one from 7 to C. So that's what the edge set of a directed graph might look like. We need to know we're working with a directed graph, so we know to interpret these pairs as ordered. The order matters. You can imagine in network science, there are a lot of cases where we care about the order. For example, we'll see in a second, is the World Wide Web. So that's the system of web pages. So our vertices are web pages. And the edges, directed edges in this case, are defined by hyperlinks from one site to another site. So hyperlinks have a direction implied by them. I click on this link on this site and I go to the other site. That's different from there being a hyperlink on that site that goes to this site, right? So there's a direction implied. There might not even be a hyperlink that goes from the other site to this one, right? So sometimes we need to take account of direction. We'll counter those. In this case, I mentioned degree in a lot of these cases. In this case, we don't just have one degree associated with each vertex. Instead, we have in degree and out degree. So let me say the in degree of, let's say, vertex 2 is however many directed edges are going into vertex 2. So from 1 to 2, from C to 2 to 7 to 2. I'm not going to count 2 to 1 or 2 to A. Those are outgoing edges. I just count the ingoing edges if I'm looking at the in degree of that vertex. So this would be 3. And let's say the out degree of vertex 2 is 2. There's 2 edges going out of it. And then there's also the sense of total degree of a vertex. Right, and it might be the case that some vertices don't have any in degree. Maybe they just have out degree, like vertex 7 here. Sometimes this is, we might write ID of 2 or OD of 2, just as shorthand and as a mathematical function. So vertex, let me look at C here. So I could also say the in degree of C. I have 1 edge going into C, so in degree of C is 1. The out degree of C is also 1 because I have 1 edge going out of it into 2. Okay. There are lots of things you can do with graphs, sort of extra stuff that you can put on them, accoutrement, various labelings and colorings that you can do with graphs. So I just want to mention that really quickly here. There is, I have this image here. You might have colored edges that represent something. Maybe there are several different types of relationship. Maybe you don't just care about whether vertices are friends or not, but maybe you have, these 2 people are friends. These other 2 are enemies. These other 2 are strangers they've never met. So you might have different kinds of relationships, and so we can use colored graphs, either edge colored or vertex colored, if your vertices maybe have some categories in which they correspond. So just not a whole lot I'm going to go into here. I just want to say that there's a lot of extra stuff you can do with graphs, different things you can put on. You can label the vertices with numbers or vectors, or I've even labeled vertices with other graphs. That was a software project I was working on. That was pretty cool. I had a big tree of graphs. There, the vertices represented graphs, and you got from a vertex to another vertex by making a little change to the graph, say deleting an edge. And so you can form this network of graphs. So that was a cool project. Just, kind of heads up, you can do other stuff with these and add things as you need them, and that'll change the analysis. And so we'll develop that in this course, what sort of analysis we can do with those extra things like labelings and colorings.